College's Intermediate Algebra online lectures. My name is Jim Helmer, and today we're going to talk about section 5.5, which is applications of rational expressions. And of course, we know that applications means story problems. And I know some of us struggle with story problems, but the key to them is reading. I put a little note here on the side of the board. When it comes to any application or story problem, whatever you want to call it, the key is to read it again, and read it again. With every story problem, you need to read it at least 3 times before we actually begin to do anything with that information. And each time we read it, we're actually looking for different pieces of information. The first time we read a problem, I tell my students it's essentially just make sure you understand the words that it's giving you. If there's a word in there that you don't know what it means, it may throw off the entire approach to what you need to do to solve this application. The second time we read it, well, let's go looking for given information. What's important that they're giving us to work with? The third time we read it is to determine, well, what's our variable? What's the missing piece? What are they asking us to find? Finally, once we've read it 3 times, we can put it all together to maybe build an equation that we can solve. And then, of course, lastly, we want to check it. Now, I also sometimes tell students after you solve the problem and maybe check it to see if your answer makes sense, well, part of checking it is to read it again. Make sure that you've answered the question and your answer makes sense. And that's how you check it. You read it essentially a 4th time and say, is my answer reasonable? Sometimes that's the best check we can do. So let's look at an example here. This application problem, being that we're in section 5.5, that should be a clue sometimes, especially in a math class, that we're working with rational expressions, we're working with proportions. So that's probably going to be the tool that I want to use to apply here. Now, first thing we're going to do is just read it. Do we understand the words? An experienced mason constructs a wall in 3 hours. The apprentice completes the wall in 6 hours. Find how long it takes if they work together. So we've read it. But maybe I want to understand, well, what's a mason? Okay, it's a bricklayer or someone who works with concrete, or it's someone in the construction industry. An apprentice is someone lower down on the ladder. Maybe they don't work as fast, they're just learning the job, so it's going to take them a little more time. And if we look at this, 3 hours compared to 6 hours, things make a little sense. So the first time I read it is, do I understand the terminology? Now, the second time I read it, let's find the given information and see what we can do with it. An experienced mason constructs a wall in 3 hours. Well, let's think about that first sentence. One wall can be built in 3 hours by the experienced mason. One wall per 3 hours. We're dealing with rational expressions, so that's the tool we're going to use. The apprentice completes the wall, and we're assuming the same wall, 6 hours. So the apprentice can do one wall in 6 hours, one wall per 6 hours. Find how long it takes if they work together. All right, so now I kind of have some idea of what it's giving me. It's telling me he can build one wall in 3 hours and he can build one wall in 6 hours, these 2 different people. Now we're going to read it the 3rd time and say, what am I supposed to do with this information? What do I need to find? The experienced mason constructs a wall in 3 hours. Let's start writing this down. One wall for 3 hours. And I'm going to put units in here because we know in application, units are important. One wall, 3 hours. All right, the apprentice completes the wall in 6 hours. One wall in 6 hours. Find how long it takes if they work together. We're asked to find how long it takes, long, so we're looking for time. That's the key word. We want to look at that and maybe underline it in the story problem. And if they work together, this is a key word. It's telling me what I need to do in order to find what I need to find. Together tells me to add. So if I add his ability to build a wall in 3 hours and the apprentice's ability to build a wall in 6 hours, if they work together, that addition. Well, what is the last question? Find how long it takes if they work together. How long does it take to build a wall if they work together? Well, one wall is all we're dealing with. and we don't know this time. This is our variable, X amount of hours. So we've read it 3 times. We were able to take the given information and what it was looking for and assign a variable and build an equation. Let's simplify this without the units. We just have a rate of 1/3 plus a rate of 1/6 equals a rate of 1 over x. It is a rational equation, right? It has some rational expressions in an equal sign, so we do have our equation. We can solve this using the methods we talked about in the previous videos. I can determine the LCD, so we're at this step right here. We're going to solve. My LCD is 6x. I'm going to multiply all the terms by 6x, so I get 2x plus x equals 6. And that's what I get when I multiply by my LCD of 6x. 6x over 3 is 2x, 6x over 6 is x, 6x over x is 6. And now we can solve that. 2x and x is 3x. And divide both sides by 3, x equals 2. Now it's time to check our solution. We can do that by reading and doing a little bit of critical thinking. An experienced mason, since he's experienced, he can do the wall in 3 hours. And the apprentice can build the wall in 6 hours. So it makes sense. He's faster because he's more experienced. He's slower, less experienced. If they work together, we have 2 people working on the job. It should be less time than if the experienced mason worked together. Is our answer less than the experienced mason? Yes. So it makes sense. It's a plausible answer. And one thing we must always check is units. When it comes to application problems, they need units. Otherwise, it's a senseless number. So our units is length of time. So we're going to have hours. And we could continue that on and say, well, it takes 2 hours for them to work together, but the main unit is hours. And we can see from this solution, and going back and reading it, does it seem plausible? Yes, it does. So I'm going to trust that if they work together, they can do it in 2 hours. And we could always go back and check it in here and make sure we didn't make any sign errors. All right, let's look at another example that's slightly different, but we're still going to use the same approach. And that approach is to read the problem, read it again, read it a 3rd time before we actually build it. And maybe there's some other tools that we can use as well. So the first thing we're going to do is start reading. It says a semi-truck travels 300 miles through the flat land. In the same amount of time, it travels 180 miles through the mountains. The rate of the truck is 20 miles per hour slower in the mountains than in the flatlands. Find both the flatland and mountain rates. So we read it the first time. Do I understand what's taking place here? Well, we have a semi-truck, and it's driving from point A to point B, and it's driving through some flatlands, and it's driving through some mountains, so we have different areas, and it's also traveling at different rates from the story. And I understand the terms, but I'm going to assess right now. Because I'm dealing with miles, and I'm dealing with time, there was same amount of time was a key word used here. And we were given something about 20 miles an hour, so we know we're given rates. We sometimes need to bring something to the table before we can solve it. And from these keywords in here, just from reading it and understanding the terminology, I'm thinking right now I'm going to have to use distance equals rate times time, a formula that we should, at this point in our math classes, maybe have memorized. So I'm going to write that right here. Distance equals rate times time. It's because I understand the terminology. This is something that I'm going to write down. Now I'm going to read it again and say, what's the given information? And maybe I can find another tool to help me solve this problem. The semi-truck travels 300 miles through the flatlands. In the same amount of time it travels 180 miles through the mountains. The rate of the truck is 20 miles per hour slower in the mountains than in the flatlands. So let's maybe help us visualize what's taking place here. Sometimes drawing an illustration and visualizing the problem can help us put together what equation we need to build. So I'm told that a semi-truck travels through the flatlands, and if you're really into the artistic aspect, you could maybe draw a good old 18-wheeler here, whatever you want to do. You get the idea, right? We don't have to be artists. So he drives through the flatlands, and then he has to drive through some winding mountains, whatever, it's increase in elevation. I'm no artist, I'll never admit to that. And then here, when we read the problem, we say, okay, well, we're told that we have a distance of 300 miles in the flatlands. And we're told we have 180 miles in the mountains. So I'm just transferring this to a picture. So he's traveling flatlands and then he's going up into the windy roads of the mountain and he traveled 180 miles. So this is my distance. What does it tell me about rate? Well, as I'm reading, I'm told his rate is 20 miles per hour slower in the mountains. So this is the second time I'm reading it. It's about the given information, what's being given to me. Well, it tells me that this through the mountains is 20 miles an hour slower. Well, 20 miles an hour slower than what? His rate in the flatlands. That just determined what my variable is. I don't know what his rate in the flatland is, but I do know that he's 20 miles an hour slower in the mountains than in the flatlands. All right, it also did tell us something about time because we recognize distance equals rate times time. What are we told about the time? The time that it takes to travel this distance at this rate is the same as this distance and this rate, because it said in the same amount of time it travels. So that means we have to do maybe a little adjusting to this equation. Well, we know time is the same regardless of where we are because the problem gave us that information. So let's manipulate this a little bit. Let's solve this for time, the given information. What's the same for both? I can divide both sides by r, so I get time equals distance over rate. This is my tool to use to solve this. I read it the third time, make sure that I set this up right, that I took the given information, I assigned the proper variable. A semi-truck travels 300 miles through the flatland in the same amount of time it travels 180 miles through the mountains. The rate of the truck is 20 miles per hour slower in the mountains than in the flatlands. Find both the flatland and mountain rates. All right, so now I'm ready to build my equation. I'm going to find this rate, the mountain and the flatland rates. And I'm going to use my tool of time being the same for both, and time is distance over rate. So I'm going to say, okay, in the flatlands, I travel 300 miles at a rate of some value x. This is my time spent in the flatlands equals my distance in the mountains over my rate in the mountains, which is the same as the flatlands, but 20 miles an hour less. So less than the flatlands. Now, if we look at this, if we recall what we saw in the last section, 5.4, we dealt with proportions. Well, we can use the cross product in order to solve this equation. We're ready to solve it. So I'm going to use the cross product and multiply our denominators to our numerators. And I'm going to get 300 times x minus 20. I have to distribute 300 times x and 300 times negative 20. And then I do the same thing here, x times 180. Well, that's just 180x. So this is actually the easy part. The hardest part was building that equation, and that was the most time consuming. We had to read, and we had to read it again. So now we're going to actually solve the easy part, right? I'm going to subtract 180 from both sides and add 6,000, and that's going to give me 120x equals 6,000, and then I'm going to divide both sides by 120, and x equals 50. 50 what? Remember, when it comes to application problems, units are crucial. While this was a rate, x was a rate, our rate is in miles per hour. And we can abbreviate in this case. We could take it further and say 50 miles per hour in a flatland. Does this answer the question? Not fully, because if we go back here, it asks for the rate of the flatland and the mountain. We want both of those rates. Well, this is only one of them. How do I find the other rate? Well, let's go back to our problem, or even the story problem. And it says the rate in the mountains is 20 miles per hour less than rate in the flatland. So that's our flatland. Our mountain was 20 miles an hour less. Well, I can just plug that in. 50 minus 20 is 30 miles per hour in the mountains. So I'm going to write mountain here and flat land here. Now, let's just check one more time to make sure, does my answer make sense? I'm going to go back and I'm going to reread the problem and say, okay, well, he's traveling through the flatlands at some speed, 50 miles an hour. And he's traveling through the mountains a shorter distance, but he's only going 30 miles an hour. Well, does this make sense so far? He can go faster in flatlands than in the mountains. Well, if I was driving a semi-truck, I'd go a little slower in the mountains because I don't want to be falling down a hill, right? So this rationally makes sense. Faster flatlands, slower in the mountains. If it was the other way around, maybe we did something wrong. And do these seem like reasonable real-world speeds? Well, 50 miles an hour, that sounds like a reasonable speed for a semi-truck. Maybe he's going a little slow. Hopefully you're not the guy behind him, right? 30 in the mountains sounds very reasonable. Now, if I got answers that were, he was flying, 500 miles an hour through the mountains or something, I'd say, hey, this is not reasonable. Maybe I did something wrong. So just check it, make sure it's a reasonable answer, and you answer all parts of the question that it asks for. So remember, read, and then build your equation and check it. Make sure it makes sense. That is section 5.5, the applications of these rational expressions in equations. Thank you.